Thanks. So, is it working? Yeah. Okay. So this is joint work with Neil Immerman, Muli Sagiv, and Sharon Shoam, and it's about invariant inference, which is a set of techniques to prove. Okay. Now is it working? Okay. So it's about invariant inference, which is a set of techniques to prove the safety of transition systems. So the system has a set of initial states, and it makes transitions over time. And we would like to prove that no reachable state is bad. A prominent way of doing this is by an inductive invariant, which is a set of states that includes the initial states, excludes all the bad states, and is closed under transitions of the system, so there is no transition from a state that satisfies the invariant to one that doesn't. Such an inductive invariant over-approximates the set of reachable states and separates it from the set of bad states, establishing safety. So for example, consider the system over n propositional variables representing a number in binary starting from 0, and in each step incremented by some even number. And we want to prove that the system never reaches the state where all bits are 1. So we can specify this, but this is not an inductive invariant because there is a transition from a state where not all bits are 1 to a state where all bits are 1. But we can strengthen this to specify that the least significant bit is not 1, which implies the safety property. And this is an inductive invariant. If you start from such a state, you also end up in such a state after a transition. So invariant inference attempts to find inductive invariants automatically. So this is automatic safety verification. And SAT-based invariant inference does this while employing a SAT solver. So there are many different ways of doing this. In this work, we are primarily motivated by the IC3 PDR approach, which in the last decade has revolutionized hardware model checking, and in a long line of work is also being applied to software verification. And looking at this list of algorithms and studying it raises all sorts of questions, like why do they succeed when they do? And when they fail, why is that? Without meaningful answers to these basic questions, it's harder, not impossible, but harder to answer the question of how can we make them better. So this work is a theoretical investigation of the complexity of invariant inference, drawing inspiration from exact learning theory to prove some pretty cool lower bounds to shed some light on invariant inference algorithms. And before I say more about these algorithms and our results, let's be very specific about the setting. So we're interested in Boolean transition systems over n propositional variables. And given a transition system from a certain class, we want to find an inductive invariant in an expressive language, so in conjunctive normal form, not merely conjunctions, but where the invariance length is bounded by some polynomial, because we can't expect inference to work efficiently if the only invariants are exponentially long. And we would like to understand the search for invariants of reasonable length in an expressive language. So as a decision problem, this is complete for the second level of the polynomial hierarchy. So it's NP-hard with access to a SAT solver. So as an example of such an algorithm, consider what we call PDR1, which is essentially PDR with just one frame. And on the example system we had before, it works like this. It starts with the candidate invariant that allows all states that are not bad and checks if it's inductive. And alas, there's a counterexample to induction, as we've seen before. So the algorithm wants to exclude the pre-state of the transition from the candidate invariant. But excluding just one state would converge very slowly, so instead we want to generalize and exclude a set of states in each iteration. And the question is how to choose this set. So the heuristic of PDR1 is to drop facts about the example as long as this wouldn't exclude states that are reachable in one step. So we write this conjunction that captures the state we want to exclude, and this is not reachable in one step, so everything is awesome. Now we say, suppose you drop this literal, would excluding the set of states that satisfy this remaining conjunction, would this exclude the state reachable in one step? And the answer is no, so we drop this literal. Same for the second literal. Still, this set is not reachable in one step, so we decide to drop this literal. But when we get to the literal about the least significant bit, excluding this set would exclude the state reachable in one step, so we don't drop the literal. And doing this for all literals gives us a clause to the invariant saying that the least significant bit is not 1, which is an inductive invariant, and there is much rejoicing. So in code, in each iteration, we check whether the current candidate is inductive, and if it's not, we obtain a counterexample to induction. This is what we call an inductiveness check. And to generalize, we perform a series of checks for reachability in one step, which we call a whole check, here with the precondition in it and the postcondition of what we want to conjoin to the invariant. And this is whether the precondition implies the postcondition under one transition of the system. And this algorithm is SAT-based because these checks are implemented using a SAT solver. Okay, so this is PDR1, and it exhibits two interesting points about real inference algorithms such as PDR. So one point is the question of how to generalize. And the heuristic in PDR1 concerns reachability in one step, but this obviously may fail for many systems. The answer in full-fledged PDR is much more complex, but still very heuristic. And we show that indeed inference is hard in general, and there's no good answer in general to the problem of generalization. But the sort of generalization that happens here does something actually incredible, and it can be stronger than all algorithms that don't use such whole checks and only rely on inductiveness checks. Okay, so to make sense of these things, we introduce the whole query model, an algorithmic model of invariant inference, where the algorithm can't directly access the program, only perform queries. So the algorithm chooses the precondition and the postcondition, sends it to the oracle, and gets in response whether the precondition implies the postcondition under one transition of the system. After a sequence of such queries, the algorithm needs to find an inductive invariant. And one of our key observations in this work is that such a black box access makes sense and can model a large class of interesting inference algorithms, including PDR. So in PDR1, these are the only places that access the program. And these can be implemented in the whole query model. So the inductiveness check is a query with precondition I and postcondition I. The reachability in one step is also a whole query. And obtaining a counterexample to induction is also possible through a linear number of queries with some sort of self-reducibility, as we explain in the paper. So we have this model that captures many interesting algorithms, and we want to understand its complexity. And the complexity measure in this model is the number of queries the algorithm needs to perform before it finds an inductive invariant. And our fundamental theorem about this model and this complexity measure is that it's hard in the general case. So in the general case, inference requires a number of queries exponential in the size of the vocabulary. And this complexity measure and this lower bound is information-based. So we only count the number of queries, and it doesn't matter what's the computational power of the algorithm to compute the queries. Even if it has unlimited computational power, it would still require an exponential number of queries. And being information-based, this lower bound is unconditional and doesn't depend on any computational complexity assumptions, such as p doesn't equal np, or things like that. And we use this result to prove our main theorem that the reached whole queries are important, and the freedom the algorithm has to choose both the precondition and the postcondition is actually very, very important. By that I mean that we can compare this more general whole query model to a more restricted case, which we call an inductiveness query model, which is also a black box model. But here the queries are of the form, so the algorithm chooses a candidate invariant, sends it to the oracle, and gets in response, congratulations, you found an inductive invariant, or computer says no, and here's a counterexample. So it's a special case, more or less, of the whole query model, where the precondition and the postcondition are always the same. And this is essentially the ice learning model from Garg et al. And the complexity measure in this model is the number of inductiveness queries the algorithm needs to perform before it finds an inductive invariant, and its worst case amongst all possible counterexamples the oracle may return. And our main theorem is that there's a gap between the general whole query model and the inductiveness query model, in the sense that there exists a class of transition systems for which there is an efficient algorithm that's based on whole queries, but every algorithm in the inductiveness query model would require an exponential number of queries. And this whole query algorithm is actually our very own PDR1, which is a simple case of PDR, which also proves that the ICE framework cannot model PDR and the extension by Wiesel et al. Is necessary. And the part in PDR1 that can't be modeled in the inductiveness query model is this check performed in the generalization of reachability in one step, where the precondition and the postconditions are not the same. Okay, so let me say a few words about the proof. So the construction works by taking all CNF formulas with at most n clauses that are monotone. That is, all variables appear only negatively. So this is an example of a formula. And each such formula induces what we call a maximal transition system. So this is a transition system that allows all transitions that are not a counterexample to the induction of the formula phi. So all the states that satisfy phi can go to all the states that satisfy phi, and states that don't satisfy phi can go wherever. So the class is the class of maximal transition systems for all monotone CNF invariants with at most n clauses. So this is the construction. And for the upper bound, PDR1 takes a quadratic number of queries, and the reason is that each iteration produces a clause of the formula phi, which is an inductive invariant for this system. And the reason for that is that in the generalization, the check of reachability in one step, because here the set of reachable states in one step is exactly phi, so this is an implication check whether phi implies what we would like to conjoin to the invariant. And generalization minimizes this, so it finds a minimal consequence of phi, and it's a property of monotone CNF formulas that minimal consequences of the formula are actual clauses, syntactic clauses of the formula. So after at most 10 iterations, this will produce phi. So this is the upper bound. For the lower bound, on the inductiveness query oracle, suppose we have an algorithm that interacts with an inductiveness query oracle running over a system that has phi as an inductive invariant, but it's some general system. And it takes many queries before it manages to find an inductive invariant. So now the claim is that this very same session is also valid against the maximal transition system for that phi. And this is because every transition of the original system for maximality is also a transition of the maximal system. And so all these counterexamples are also present against the maximal system. And hence, the complexity of inferring an invariant for the maximal system is at least as that for the original more general system, which in general shows that inferring invariants for maximal systems for monotone CNF invariants is at least as hard as learning general systems for monotone CNF invariants. And this requires an exponential number of inductiveness queries and actually also an exponential number of Hall queries, as we show in the fundamental hardness of the model. What doesn't hold in the Hall query model is the inequality between maximal systems and general systems. So this is the lower bound, and we managed to find a class on which there is efficient inference algorithm in the Hall query model, but no efficient inference algorithm in the inductiveness query model. So the end is near, but before that, I would like to remark that this truly exponential lower bound is quite unusual in exact concept learning. And it attests to the inherent ambiguity of counterexamples to induction, because you don't know whether the example should be part of the invariant or shouldn't be part of it. So this actually shows that learning from counterexamples to induction is harder than learning from examples labeled positive or negative, which more generally shows that the complexity of counterexample guided inductive synthesis depends on the form of counterexample. So overall, we studied the complexity of inferring invariants of polynomial length in a black box model based on Hall queries. We showed that it's hard in the general case and requires a number of queries exponential in the size of the vocabulary, that the use of rich Hall queries where the precondition and the postcondition are not the same is important for inference and generalization, and that learning from counterexamples to induction is harder than classical learning from positive and negative examples. Thanks.
We have plenty of time for questions. Did I see a hand? Okay.
Thank you very much for the talk. So I think I have a question about how you model PDR. So I think in the PDR implementation, there's also one thing that's generalizing the counter example to induction through ternary simulation of the circuits. And I wonder if that will break the assumption of, for example, treating the system as a black box and
Right. So this model can't model very well ternary simulation, but many other forms of PDR can be captured by this model.
Any more questions? How strong is your restriction of transition systems to Boolean transition systems? And would these results generalize if you lift that restriction in some way?
Right. So that's a very good question, and we also asked ourselves. So here in this work, we focused more on the Boolean structure and the complexity of handling this. We also wanted to extend these results to EPR because, why not? And then we realized that all the propositional things are just a special case, so there's nothing really interesting coming there. So I guess I would say that it would be interesting to find new sources of complexity stemming from the infinite state.
Any more questions? Yes.
Thank you for the talk. Could you explain how the power of examples labeled positive and negative are exactly more powerful than the counter examples?
Yeah.
Because I didn't get that part exactly.
So I have a slide. So now in the setting of exact concept learning, so there's some unknown formula we want to learn, and we perform equivalence queries. So we ask, is it alpha 1, is it alpha 2, and so forth, until we manage to find this unknown formula. Okay. And now, what are these counterexamples? So classically, its examples, the counterexamples the Oracle returns are things that you know whether the target unknown concept, whether these are models of the concept or not. And counterexamples to induction is actually a pair of examples. One of them is negative and the other is positive, and you don't know which is which. So if you consider the complexity of learning monotone CNF formulas with at most n clauses, so the classical result is that the complexity here is sub-exponential, even polynomial if you allow exponentially long queries. And this work shows that for counterexamples to induction, this is truly exponential. So there's a gap between learning from positive negative examples and learning from counterexamples to induction.
Thank you.
One more question we have. Hopefully it's quick.
Do you observe some similarity of your result about positive and negative sample to Angloin style automata learning one? So I remember there was some result about automata learning from examples, and the automata learning from example and counterexample has a kind of a complexity gap.
Yeah, so the setting here comes directly from Angloin, and the result about the classical results. Parts of the classical results come from Angloin and later work, and that's definitely a large part of the inspiration for this way of modeling and this way of analysis.
Okay, I'm sorry, we'll have to take the rest of the questions offline. Let's thank Yotam again.